Okay, so we're on to P11 now, which is static electricity. So we're going to be looking at how electrons affect different surfaces when they move from one surface to another. Okay, but let's define a couple of terms. So an electrical conductor is a material that electrons can move through or pass through. An electrical insulator does the opposite. Okay, so electrons struggle to actually pass through that material. If two insulators are rubbed together, the force of friction will knock electrons from one material onto the other. Okay, so obviously you will not know which surfaces or which materials are more likely to pass their electrons onto the other, and vice versa, but you should know that the only particle that can move is going to be the negative electron, because we've said in a previous video that it's actually a lot more lighter than the protons and neutrons in the nucleus, and also the electrons are located on the outside of the atom. Okay. So again, this movement of electrons wouldn't work with a conductor because the electrons would literally move through the metal. Okay, so in a conductor, the electrons freely move through the conductor, whereas in an insulator, they don't move, and therefore friction will cause them to actually leave the surface. So a material will become negatively charged if it gains electrons, and if it loses electrons, it will become positively charged due to the remaining positive protons. Okay, and again, size of the positive charge will be the same as the size of the negative charge. Again, so kind of similar to magnets. Okay, opposite poles, but in this case, opposite charges or opposite signs attract. So here we go, a minus and a plus sign attracting, and a plus and a minus sign attracting. Okay, if you get two signs the same, they repel. Okay, the earth ground, okay, wire, remember we talked about in the previous video, has a voltage of 0 volts, and uncharged objects have a voltage of 0 volts as well. Okay, air is an insulator as well of electricity, so if you make a circuit in your classroom, and if you break the connection, let's say, I don't know, you split the wire, electricity is no longer going to pass through that circuit because obviously air is in between the wires. Okay, if an object becomes charged, it will have a voltage. Okay, so just bear in mind that we can get a voltage if there's an excess positive charge or an excess negative charge. Okay, the bigger the charge that builds up, the bigger the voltage, obviously. If a charged object comes close to an uncharged object, the charge can jump across the gap, leaving both of the objects uncharged. When this happens, we see a spark. The bigger the voltage has been built up, the larger the distance that the electrons can jump, and this process is literally what happens in lightning. Okay, it's just on a larger scale. How does this happen? Well, essentially you've got the clouds moving past each other. Friction between the surfaces causes the electrons to be moved. Okay, so eventually you're going to get that excess build-up of negative charges on the bottom lower surface of the clouds, which then be attracted naturally to the ground. Okay, it's just something that happens. Electrons are at a more stable state when they're actually on the ground or in the earth. Okay. What are the dangers of lightning? Well, it obviously can cause fires, it can kill people, it strikes them. Now, you may hear obviously people that have survived lightning strikes. Yes, it's definitely possible, but it also can kill people, okay? Right, charged objects can attract neutral objects if the charges can move a little. So let's have a look at this diagram here. So if we have passed on electrons onto this balloon, okay, so notice it's negatively charged. Okay, so we've rubbed it on, I don't know, a woolly jumper or something, and the electrons from the woolly jumper has passed onto this balloon. Okay, as we drag this balloon to this wall, okay, remember the electrons are light and they are on the outside of the atom. So electrons, as opposed to protons and neutrons, are going to be particles that are more likely to move. We know that like charges will repel. So what we've got here we've got like charges being repelled. So initially we had plus minus, plus minus, plus minus. So we had neutral atoms on the end of the wall here. Okay, but the negative charge from this balloon pushes the negative electrons to the right here. So that we're left with an excess positive charge, the protons here. Okay, but we know a negative and a positive charge will attract, okay, like it says here. So therefore the balloon sticks to the wall. Okay, so you need to be able to explain this in your exam. Okay, so let's talk specifically what earthing means. Okay, so we know that it's going to be a conductor, okay, that is connected to the particular object and to the ground or the earth. Okay, now there's two ways that you can earth something. So if an object gains a negative charge, so excess negative charge, then to earth it, electrons will flow from that object to the earth, okay, to the ground. However, if the object has an excess positive charge, the opposite is going to happen. We're going to get electrons flowing from the earth to the object to neutralize it, okay? So essentially, the point is the object's always going to become neutral, okay? Because that's the only way that the electrons are going to be stable and the atoms are going to be stable. So let's have a look at some uses for electrostatics, right? So let's look at painting, okay? So in this case, the paint droplets are going to all have the same charge, okay? That makes the droplets repel each other, so the paint droplets are going to be spread out, which means when they actually flow onto the car panel, it's going to be in a nice even layer, okay? But also, in order to ensure that the paint droplets actually get to the car panel is going to be oppositely charged, okay? So I don't know, the paint droplets could be negatively charged. That would mean the car panel would be positively charged, okay? It doesn't matter what charges they are initially, as long as they're oppositely charged, okay? And again, why is this useful for us? It means that the paint layer is evenly spread out, okay? You can use this in crop spraying as well, okay? So you need to be able to describe this principle in your exam. Right, some dangers. Explain why static electricity is dangerous when filling up petrol tanks. Well, it could cause a spark, which could ignite the fuel and cause an explosion. Okay, pretty straightforward. Remember, petroleum, the fumes are highly flammable. So how could we prevent this? Well, we could earth the vehicle, or we could place a conductor next to the pump, so that means that that excess charge will travel through the conductor and obviously not heat up the flammable petroleum, okay, fumes. Okay, so what are some other dangers of sparking? Well, we can have some additional fires being started, okay, if there's materials that are also flammable close by, and if there are humans present, obviously they're going to get some harm done onto their body, so serious skin burns, okay, so, you know, those are some things you can write down in your exam. So, what is an electric field? Well, essentially, it's the region or area around one charge where another electric charge will feel a force. Okay, so if we look at these diagrams here, so we've got a positive charge here. Notice the direction that these lines are making. They're going outwards, okay? And essentially, what you need to remember with electric field lines, because that's what these are, they're the direction that another positive charge, if we placed another positive charge there, would go in, okay? So that means they point in the direction that a negative charge would go in, okay? Let's have a look at this one. So here we go, we've got a negative charge here. If you placed a positive charge here, it would obviously move towards that negative charge, okay? Like these electric field lines are showing us, okay? So it's the opposite direction that a negative charge would move in, because if a negative charge was placed here, it would feel a force going the opposite way, because we know like charges repel. These are what we call radial electric field lines, okay, because they're radially spreading out from this spherical charge, whereas this is what we call a linear field lines, okay, so notice they're all parallel to each other, okay, and we get this when we have two surfaces, one surface full of positive charges and another surface full of negative charges, and again notice the direction of the line. It's going from the positive end to the negative end, okay? It's the direction a positive charge would take, okay? A couple of things you should be aware of with field lines. If we've got a high concentration of them, okay, it means there's a lot of positive charges in this sphere, okay? If there was less, then the concentration of the lines would be less. And also, you can also see the closer we are to the center of this positive charge, look how close the lines are together, as opposed to if I went further out, they would be further apart. Okay, so the concentration of the lines determines the strength of the electric field. Same principle here as well. Okay. Again, you know, these show a weaker electric field, weaker electric field. Now, one thing you should be able to do is to draw some electric field lines or sketch them in your exam. Okay, so they might give you two positive charges and you would have to draw the electric field lines. So look carefully. So obviously this side is essentially pretty much the same as this. Okay, they're radially being spread out. Same on this side as well. But we also know that positive charges will repel. So what is actually happening to the electric field lines? Well, let's look. Notice they never actually touch each other. Okay? So you need to make sure you draw, yes, they're coming out of our positive spheres, but make sure they never actually touch. Okay? And because they never actually touch, it means that these positive charges also in reality don't touch either. Same is true for the if we draw two negative charges, okay, literally same lines, but you need to make sure that the arrows are going in the opposite direction, okay? So that the direction that the positive charge would move in, okay? So the positive charges will be attracted to the negative charges. But again, these lines don't touch, meaning in reality they will actually also physically not touch. They'll move away from each other. Again, now, what happens if they do attract? Similar to these linear field lines here, okay? They're going from the positive end to the negative end. Here we go. We're getting this line here going from the positive spherical charge to the negative spherical charge here. But because they're spheres and not a long plank of a long line of charges, they follow this curving nature. Okay, so please make sure you draw your lines kind of like a magnet. Okay, but notice here this line on this side is still going radially out, as well as this one here. Okay, it's going radially in. Okay, but this is the form that the electric fields, the field lines would take between a positive and a negative charge. And if we change the signs, the lines would be the same, but we just reverse the arrows, okay? So that's all you need to know for P11.